Alrighty, so let's look at some properties. So this is still 4.1. Let's look at some properties of integrals. And lots of them still work. So, so the first is just that now if you specify a path, it doesn't matter how you specify it. So that's if gamma of t and sigma of t are different parameterizations of the same path. Okay, so for instance, what we use that straight line to get out to let's see, we use that straight line to get out to 1 plus I. And so, for example, x equal t, y equal t for 0 less than or equal to t less than or equal to 1 gives a line from 0 to 1 plus I. But x equal t, y equal 2t, 0 less than or equal to t less than or equal to half does as well. Okay, so both of those are a straight line from 0 to 1 plus I. So it's the same path, it's just different parameterizations. So now let's go back to example 4.1 and we'll use A here since we're using the straight line. Okay, remember that of course you don't remember, but you can look it up. That gamma of t is equal to t plus it, 0 less than or equal to t less than or equal to 1, and f of z equals z bar squared. We got an answer of 2 times 1 minus I over 3. Okay, so we got that for the first one, the path we already knew. Okay, but now, so sigma of t is equal to 2t plus I 2t, and that goes from 0 less than or equal to t less than or equal to a half. Sigma prime of t is equal to 2 plus 2i. Okay, so now if we do that integral, we go, if we're doing sigma of f of z dz, that's equal to the integral from 0 to 1/2 of 2t, we need the conjugate again, so minus 2ti squared, and then times 2 plus 2i dt. So this is equal to 2 plus 2i all times the integral from 0 to 1 of this thing in here. So we square it again, so we have 4t squared. Mixed terms, we get minus 8, I guess, 8t squared I. And then the last term again is a negative, so it's negative 4t squared dt. And so that's 2 plus 2i, 4t minus 4t squared minus 4t squared just goes away, and so I'm just integrating that term, and so that is minus 8 thirds t cubed I from 0 to 1/2. Well, 0, you get 0. So it's just this part. Oops. Well, minus and a plus here. Sorry. So t cubed would be t over 8. So it looks like we get 2 plus 2i, and then plus 1, right? 1, yeah. So, or, well, no, minus. Or minus 1/3 I. And so, let's see. Just checking my stuff here to make sure let's what we have here, 2/3. I'm slightly confused as to I just want to make sure I did that right. So that was the 2 plus 2i. Oh, no. Yeah. Wait, no, there's minus. Yeah, minus. I did minus 2ti. Yeah, okay. And you get 4 there, you get the 4 there, and it is a minus, and you get the 8, right? Because you get 4t squared, but 2 of those, so minus 8t squared I. Yeah, that looks good. And I factored out the 2 plus 2i. Yeah. Okay, so then this is let's see. I don't know, something seems fishy here. So what do I get? I get, if I pull out the 2, I get 1 plus I, like that. Minus, well, so let me just write it this way. Sorry about that, but you know, all of a sudden I'm looking at this going, I don't like what I'm getting here. 2, and then this is 6 thirds I. So see, that would say that's plus 5 thirds I. So I oh. So again, yell at me, people. So back here, I had this step that you see with the 2 plus 2i times everything, and then all of a sudden, for some reason, I thought I was adding. I don't know why. So it was just a subtraction. So a multiplication of a negative number. Okay, so this is times a negative I over 3. I knew something just didn't look right. And so now we can factor out the 2. And so we get 2/3. And then multiplying through by the I again, I get 1 minus I, which is what we got back here. A lot easier back here than we said. Let's see. Where was it? I said, oh yeah, we got 2/3 1 minus I, and so that's what we have there. Whew. Sorry about that. Now, so 4.6 gives a bunch of properties. So one of the properties is just saying that, hey, if I want to do f plus a constant times g. Now, we could put a constant times f as well, and so forth. This is just sort of a minimalist approach, saying that, oh, if I can do this, then I could do similar things like it. I could put the c on the f instead of the g, because one's as good as the other. So this is equal to, and we just break it into two integrals, so f and then plus, and we can factor the c out of the integral, so g over gamma, like that. So that's the first property, is that we can split these integrals up and we can factor a constant out. So same as real numbers. Then another is, if you traversed gamma backward, this is backward, and use that parameterization to do this integral f, you would get the negative of the positive integral f with the positive orientation of gamma there. Okay, so going backward over something just gives you the negative, or well, really the way to look at it is going opposite directions. You know, one will give you a negative, the other will give you a positive, depending on what those directions were and what the functions were. Okay, now here C is the piecewise idea. So you've got maybe two paths here. So there's gamma 1, gamma 2, and they split right there, or come together right there, really. But you know, and that's their meeting point. And so if we designate that whole path as gamma 1, gamma 2, like that, of f, well, we've already done this once. That's just the gamma 1 of f plus gamma 2 of f. Okay, so not real earth-shattering there. Now here, I'm going to go ahead and do the property and then talk about the length here. And it says, if I want the absolute value of this integral, well, I may or may not know what it is, but I can tell you this: it's less than or equal to the maximum of the absolute value of f of z for all the z that are part of that gamma path, and then times the length of gamma. So in other words, you know, if I'm going here along this path from A to B, and I'd like to know in absolute value what do I get. Well, if it could be hard to do or something, but what this says is I can just look along this path at the values of f and find the biggest, you know, maybe that occurred right there, max, absolute value of f of z. Well, now you see, if I just assume it's a constant value of f through the whole thing of this value, well then yeah, I just need to take that value times the length. Okay, so let's look at length. The length of gamma is defined as the integral from t1 to t2 of the absolute value of gamma prime of t dt. And actually, so remember, there's a real part, so there's sort of the gamma prime x and then plus I gamma prime y. Okay, that's inside there, that's that parameterization. If I want the magnitude of that, right, well, by definition, that's equal to the square root of gamma x prime squared plus gamma y prime squared. Okay, so it's just like real numbers that way, is that another way to write this would be the square root of x prime of t squared plus y prime of t squared, like that. Okay, you can either call it the real part and the imaginary part of the gamma path, or you can just say, well, x is some function of t and y is some function of t, and we took their derivatives, and that's how we got the arc length. And so these are like arc length problems from I think chapter 7 of the calculus text, and then again in chapter 10. So we do arc length a couple of times in that textbook. And so let's see, let's go back to that same sort of example that we've been using, but here I guess I don't have the book open in front of me, but this I think is example 4.4, but it's that same path. So let gamma of t 4.1a, that path, t plus it 0 less than or equal to t less than or equal to 1, and then again gamma prime of t is 1 plus I. So here our length of gamma is the integral from 0 to 1 of magnitude of 1 plus I, because that's our gamma prime, dt. Well, that's equal to integral from 0 to 1, and this is the square root of 1 squared plus 1 squared dt. So that's the integral from 0 to 1 of square root of 2 dt, which indeed is just the square root of 2. And yeah, we said it's a straight line going out here like this. This is 1, that's 1, so the Pythagorean theorem says that's the square root of 2. So at least on that one we got the length right. Let's go down here to example 4.5. And here we're going to do a circle, let gamma of t equal e to the it, 0 less than or equal to t less than or equal to 2 pi. So gamma prime is equal to e to the it times I, so I e to the it, like that. And so now the length of gamma is equal to the integral from 0 to 2 pi, the absolute value of I e to the it dt. Now this is the same thing as the integral from 0 to 2 pi, absolute value of I, absolute value of e to the it dt, and both of those are 1, so this is the integral from 0 to 2 pi of 1 dt, and we get then 2 pi. Okay, so this had a circle, a radius, this was a circle, radius 1, 2 pi r to get the circumference, and we have 2 pi. Alright, so that finishes up section 4.1, and so we'll stop there. Let's see, I have to hit escape.